Hello and welcome back to ChemClips by Mr. B. In today's video, we'll be focusing on tackling one of the trickier questions I've seen for the ideal gas equation. So let's have a crack at it. Let's see what we can do. So we're told that a student determined the relative molecular mass, the MR, of an unknown volatile liquid Y, volatile meaning it easily evaporates, in an experiment as shown in the diagram. The student used a hypodermic syringe to inject a sample of liquid Y into a gas syringe in an oven. At the temperature of the oven, liquid Y vaporized. The student's results are shown in the table. So here's the setup. We've got a simple syringe. It's injecting a sample of Y into a gas syringe, and this is placed within an oven. So we're given some information. We're told the mass of the hypodermic syringe and liquid Y before and after injection. So that's before, this is after. So clearly we've injected the difference between the two, which is 0.21 grams. We're told the oven temperature as 98.1 degrees Celsius, the atmospheric pressure 102 kilopascals, and the increase in volume in the gas range as 85.0 centimeters cubed. We're asked to define the relative molecular mass, and we're asked to use the experimental results in the table to determine the relative molecular mass of Y, and we're asked to use the gas constant 8.31 joules per Kelvin per mole. So again, it gives us in the question, it tells us in the question that R is 8.31, suggesting to us that we're going to have to use the ideal gas equation. So what is the ideal gas equation? PV equals nRT. When it comes to equations, always show the equation. Okay, so let's have a look. I'm asked to work out the relative molecular mass. If I'm asked to work out the relative molecular mass, the nearest term I'm going to calculate in my ideal gas equation is going to be moles. Why is it going to be the moles? Well, I can work out the MR from the moles. So let's rearrange this equation to give us N. So N is equal to PV over RT. And now it's a matter of substituting the data. So let's see. P, we're told that P is 102 kilopascals, but we need to be cautious. The ideal gas equation requires us to use pressure in pascals. So to turn something from kilopascals to pascals, we have to multiply by 10 to the power 3. So we've got 102 times 10 to the 3 pascals. We're going to multiply by the volume. Now the volume is given as 85.0 centimeters cubed. But again, that needs to be shown in the calculation in units of meters cubed. So how do we convert from centimeters cubed to meters cubed? Multiply by 10 to the minus 6. So multiply by 10 to the minus 6. And we're going to divide it by RT. We're told that R is 8.31. Multiplied by T, which is 98.1. But this is given to us in degrees Celsius. We need it to be in Kelvin. How do you convert something from degrees Celsius to Kelvin? At 273. So at 273. Now, if we do this, we're going to get, for our numerator, 8.67. And for our denominator, we're going to get 3083.841. Okay, so I'm going to stick this in a calculator and we're going to end up, let's see what we get for the answer, 8.67 divided by 3 or 83.841. And I end up with 2.81 times 10 to the minus 3 mole. That's what worked out. So how does this help us work out the relative molecular mass? We know that moles is equal to mass over MR. So N is equal to M over MR. Therefore, MR is equal to N over, that's M over N. We know the mass as 0.21 grams because that's how much Y was inserted into the gas syringe within the oven. So that's going to be 0.21 divided by the moles as 2.81 times 10 to the minus 3. And we get, for this question, 0.21 divided by answer equals to 74.7. 74.7. That's to 3 sig figs. Now, this is in units of grams per mole. That's what MR is measured in. So we've got the MR, we've worked out the MR. We haven't given the definition for the term relative molecular mass, but the relative molecular mass is simply defined as the weighted mean mass of a molecule, of a compound, relative to 1/12 the mass of a carbon-12 atom. So that would be our mark for the definition. You're going to get 4 marks for the rest of the question. You're going to get 1 mark for subbing your data, so you get the this stuff over here. You're going to get a mark for the free conversions for temperature, degrees Celsius, and of course for the pressure. So you're going to get another mark there. You're going to get a mark for working out the moles, and you're going to get a mark for working out correctly the MR. So that's 5 marks there. Okay, so moving on to part B. Some of the liquid injected did not evaporate because it dripped into the gas syringe nozzle outside the oven. Explain how this would affect the result of the MR of Y calculated. So how would it affect the value of the MR calculated from the experimental value? Well, we have to consider this. If some of the volatile liquid dripped outside of the gas syringe, then that means the volume of gas collected in the gas syringe is going to be lower. If the volume collected in the gas syringe is going to be lower, and we know that N is equal to PV over RT, if V decreases, that's the volume in the gas syringe, then therefore N, the moles, will also decrease. So we know that N is equal to M over MR. We know that MR is equal to M over N. We've just established that if the moles are decreasing, if that value is getting smaller, the denominator is getting smaller, yet M stays the same, where M is 0.21, then that means that the value of MR is going to increase because the numerator remains the same value, yet the denominator is decreasing. So we're going to have a large number for the MR. So MR would increase as the volume in the gas syringe, the volume of gas in the gas syringe decreases. And we've shown the mathematical steps. We've shown what happens as one variable increases or the other decreases. I hope that helped. I'll see you until next time. Bye.